This is a training module on the Texas Instruments INA333 Zero Drift Instrumentation Amplifier. Welcome to the training module on INA333 Zero Drift Instrumentation Amplifier. This training module introduces TI's Zero Drift technology and INA333 Zero Drift Instrumentation Amplifier. One of TI's main innovative focuses over the last several years has been in zero drift technology using chopper amplifier circuitry to minimize voltage offset and drift. Chopper amplifiers themselves are not necessarily a new idea. The first chopper amplifier patent was filed in 1949. These earliest implementations of the chopper amplifiers are using mechanical vibrators to chop the DC input signal to create an AC signal. The AC signal was then amplified via tube/valve circuitry and synchronously rectified to recover the DC component. This technique did provide very low offset voltage and very low offset voltage drift, but it really had very poor bandwidth. It also added considerable high-frequency chopping noise that required additional filtering and further limited the useful bandwidth of the amplifier. More modern implementations of zero drift technology are quite common now in the analog industry. The essential element of a modern chopper amplifier is an input stage with synchronous commutation of the input and the output. The DC offset of the amplifier stage is effectively inverted on each half cycle, which results in the averaging of the offset voltage to zero. An unavoidable artifact of the chopping process, however, is spurious noise produced by the chopper stabilization circuitry that is a correlated systematic noise harmonically related to the chopping frequency. Symmetric divide by 2 clocking creates only odd order harmonics, but these leftover odd order harmonic noises earns the modern chopper topology a reputation as being fundamentally noisy and limits its use in noise sensitive applications. Texas Instruments introduced a zero-drift chopping topology to solve these problems. Instead of the noisy odd-order harmonics, TI designs incorporate a proprietary synchronous notch filter to attenuate the chopping noise inherent in the zero-drift design and filter out the odd-order harmonics. The result is that the chopping noise is reduced to far below the broadband noise of the amplifier. TI's zero-drift products achieve industry-leading noise performance. Because of TI's zero-drift implementation, TI has become one of the technology leaders in the zero-drift application. Devices in the zero-drift family include operational amplifiers such as the OPA333, current shunt monitors like the INA210 family, and instrumentation amplifiers like INA333, which we will introduce in details in the rest of the pages. The INA333 zero-drift topology expands on TI's already well-balanced, low-power single-supply instrumentation amplifier family, featuring devices with wide bandwidth, rail-to-rail outputs, common mode input voltage to ground, high common mode rejection ratios, and shutdown capability. The zero drift INA333 offers the lowest power, lowest input bias current, and best overall voltage offset/drift combination of any low single supply instrumentation amplifier on the market. Designed with TI's zero-drift technology, the INA333 low-offset drift combination makes it ideal for applications requiring the best long-term stability achievable. And with a proprietary design technique to attenuate chopping noise, the INA333 also achieves industry-leading noise performance in the low power, low offset instrumentation amplifier submarket. With a supply current of 75 microamps, that is 10% lower than its closest competition, and being capable of running on a single 1.8 volt supply, the INA333 will be the easy choice for analog designers being pushed for lower power, more efficient solutions. And with only 200 picoamps input bias current, the INA333 also can be used in high impedance applications where low power and low voltage offset instrumentation amplifiers have never gone before. The INA333 targets a wide variety of precision, low-power applications, such as portable medical and portable instrumentation. However, the INA333 is also important for other major markets, such as data acquisition and weigh scales, because of its breakthrough capability of achieving low power and bias current without compromising its offset stability, CMRR, or noise. If the application requires a single supply instrumentation amplifier, the INA333 is a great place to start. The figure shows the basic connections required for operation of the INA333. Good layout practice mandates the use of bypass capacitors placed close to the device pins as shown. The output of the INA333 is referred to the output reference voltage terminal, REF, which is normally grounded. Gain of the INA333 is set by a single external resistor, RG, connected between pins 1 and 8. The stability and temperature drift of the external gain setting resistor, RG, also affects gain. To ensure stability, avoid parasitic capacitance of more than a few picofarads at the RG connections. The INA333 can be operated on power supplies as low as 0.9 volts. Most parameters vary only slightly throughout the supply voltage range. Operation at very low supply voltages requires careful attention to assure that the input voltages remain within the linear range. Voltage swing requirements of internal nodes limit the input common mode range with low power supply voltage. The four figures show the range of linear operations for various supply voltages and gains. The INA333 can be used on single power supplies of plus 1.8 volts to plus 5.5 volts. The figure illustrates a basic single supply circuit. The output ref terminal is connected to mid-supply. Zero differential input voltage demands an output voltage of mid-supply. Actual output voltage swing is limited to approximately 50 millivolts above ground. When the load is referred to ground as shown with single supply operation, Vn plus and Vn minus must both be 0.1 volts above ground for linear operation. For instance, the inverting input cannot be connected to ground to measure a voltage connected to the non-inverting input. One application of particular interest for the INA333 is portable ECG systems or heart rate monitors. In an ECG application, the action potential created by the heart wall contraction spreads electrical currents from the heart throughout the body. This creates different potentials at different points on the body, which can be sensed by electrodes on the skin surface. The signal amplitude is generally around 1 to 2 millivolts peak to peak, with measurement difficulties coming in due to the presence of large DC offsets from the electrode to skin interface and 50 to 60 Hz noise interference from power supplies, RF interference, or even pacemakers, for example. The INA333 offers high 100 dB CMRR to reduce the 50/60 Hz line noise common to both inputs, as well as offering 20 microvolts of offset, keeping the measurement error below 2% on a 1 millivolt signal. Additionally, the 75 microamp supply current and 1.8 volt supply enables maximum power efficiency and extends the life of the battery. Another good example of an application that will benefit from the INA333 are weigh scales or bridge sensor systems. In a bridge sensor system, normally full-scale output voltages are in the 10 millivolts to 100 millivolt range, or 2 millivolts per volt of excitation, and need to be amplified in a data acquisition system. The key role of the instrumentation amplifier is to amplify the very small differential input voltage and reject the common mode input voltage. But for the best performance, the instrumentation amplifier must have excellent long-term stability with regards to offset drift and gain, because real-world sensors have span and offset errors that are ever-changing over temperature. Also, many bridge pressure sensors have a nonlinear output with applied force. Here, the accuracy of the amplified input signal must be guaranteed over years of operation. A zero-drift instrumentation amplifier, such as the INA333, easily meets these stringent requirements by achieving an offset drift of 0.05 microvolts per degree centigrade.